Welcome to this lecture on time rates or related rates. So today we're going to talk about two things, which are actually just the same, time rates or related rates. Now, these are called time rates because we're going to talk about derivatives that are all with respect to time. So we're interested in things that are changing with time. Also, we're going to find out that these rates are usually solved by finding out other variables or the rate of other variables and how it affects the rates that we're interested with. Okay, so why is it important that we should know time rates? Well, the reason is that there are a lot of things out there that requires us to find the rate with respect to time. Take, for example, interest rates in businesses or loans or things like that. They are values of or percentages of money or capital that would change over time. So at least you want to know how fast those values would change over time. Another common example will be your position. Position would most likely change over time. Say, for example, for a moving vehicle, where you can see you have your speedometer. Speedometer measures the time rate of your position. And in robotics, for example, you could also have some things that measure the rate at which some bodies rotate. So, for example, you could have angular rates or the angular speed of objects. So, for example, if you want to measure how fast does a portion of a robot arm moves, then you have to know the angular rate of that that segment or that part of the robot. So those things are all with respect to time. Now, commonly we don't really restrict derivatives to be with respect to time. But now let's dive into this one and see what are the possible applications when you want to find time rates. Okay. Now, typically when you solve time rates, they are solved by finding out the relationship with other variables. So it's not just a value that you're gonna solve it plugging in some numbers, but rather it's not really always straightforward because you sometimes need equations where in the equation you need the rates of other variables and see how it affects other variables. Okay, so before that one, I just wanna introduce to you what is the typical derivative operation when you do time rates, because yes, time rates are still derivatives, but it's a bit different than what we usually do in terms of derivatives. Now, say for example, if we have the expression here x, let me change the color to perhaps black first. Okay, so let me change this into, let's wait. Okay, thanks. There you go. So now you have x. Okay, it's not enough. Maybe I should zoom out. I'm not really used to this app. Okay, so let's try this again. So perhaps I give you this equation: x plus maybe y squared is equals to 1. Now, when we wish to know the derivatives, we typically do this one. We typically want to find dy dx, or the rate of y with respect to x. Notice that this is not with respect to time. So the way that we would usually do this one, if y is not explicitly expressed in terms of x, then we perform what we call the implicit differentiation. So I think you all already know this one. So implicit differentiation. So we want to find the implicit derivatives. Okay. So how do we find implicit derivatives? Well, it's simple. Just treat x regularly, and whenever you want the derivative of y, you place a dy over dx. Okay. So just a quick example here. So if I want to find the derivative of this one, this will become 1, derivative of x with respect to x. And then this one is going to use the chain rule. This will become 2y. The power becomes 1. You don't need to write that 1. But the derivative of the inside term is y, or the derivative of y. So therefore, you have to write dy dx. And all of that is with respect to x. Now, of course, the derivative of 1 is 0. So you write 0 right there. Okay. Now, you can solve for dy over dx, which is the derivative of y with respect to x, is just given by negative 1 over 2y. And that's it. That's how you find the implicit derivatives. But how about if we perform the derivatives with respect to time? So now, when you do that one, you're going to introduce a new variable, which is time. So commonly, we use the variable t to represent time. So let's try this again. So for example, you wish to know the rate at which these variables change with respect to time. So that's the time rate derivatives right there. So now, instead of treating everything to be derivatives in terms of x, it's not always going to be with respect to time. Again, we're going to say the variable for time is t. Okay, so in that case, if I now want the derivative of x, I have to write dx dt. Okay, and not anymore 1, because now we're not taking the derivative now with respect to x, but rather with respect to t. And nothing will change this here that much. This will still be 2y. But now something will change. This will be dy with respect to time. Again, everything has to be with respect to time. 1 is still 0 even if we take the derivative with respect to time, since it's a constant. It wouldn't change with respect to time. So now, as you can see, you have an expression that contains two rates right there. When I say two rates, we're referring to your dx dt, and the other one is dy dt. Okay, so let's try this again. So these two rates right there are, well, they're coupled to each other. When I say coupled, when one of them changes, the other should also change because they're related in a single equation. And now that is the reason why we call them, again, that's the reason why we call them related rates, because one of those rates, when it changes, it's gonna affect the other one. Okay, and that's the essence of this topic. Time rates are all like that. It's the derivative with respect to time. You do it like the implicit derivative, but everything has to be with respect to time. And the challenge is that the usual topic here is you want to find out what is the rate or the value of a rate of certain things or a certain variable in an equation with respect, or not with respect, but rather if you are given with the value of the rates of other parts of the equation. To best illustrate this one, maybe let's take a look at some examples here that I've prepared beforehand. You can find this in your notes that I've sent, but this is just to illustrate to you the thought process in solving these kinds of things. Let's start with something simple. I'm just gonna copy some problems here from my other screen. So this one is a geometric problem, and you'll find that most of these things in time rates are, well, geometric problems. Okay, so not all, but most. I'm not saying it's just all for geometric problems, but rather it's the usual case. So let me just try and copy this first. I have it on my other screen, and then let's see if this works. Okay, so now, yeah, here we go. Okay, so now we have this problem. Okay, it says here, a balloon leaving the ground from 60 feet from an observer rises vertically. So let's assume there's no wind out there. It's not affected by the external stuff. So it's just the balloon going vertically upwards at a rate of 10 feet per second. Now the question is, how fast is the balloon receding from the observer after 8 seconds? So as you can tell, we're not looking for another rate with respect to time. So it's saying how fast the balloon is receding. Usually when we say how fast, that is in terms of speed. So that's distance with respect to time. Now, that distance right there, as you can see on the figure, that's represented by the variable s. As you can tell, it's the one right here. Okay, let's just say s is the separation between the observer right here and then the balloon. Okay, now for ease of solving this one, let's represent all of these things with variables. Now we know the balloon is rising, so that must be a variable right there. So we call this h, or the height of the balloon at a certain moment in time. Now also, it was stated in the problem that the person and the balloon has a horizontal distance between them, which is of 60 feet. Now, how do you start solving these kinds of scenarios right here? So typically, this is what we do. When we solve these kinds of things, what we usually do is that we first find an equation that relates the things that we want with the things that are given. So here we're given we're looking for the rate of s, and then we're given the rate of h. So that's a good starting point, because now our next goal is to find out how can we relate the variable s to the variable h. And now that can be easily done if you really just take a look at the figure that resembles, well, what do you think? It resembles it's a right triangle. Okay, so let me change this one. So you have a right triangle here, is where you have the hypotenuse equal to s, and one of the legs is equals to h, and then of course one of your Another leg here on the base, perhaps called in the base, is just the variable s. Sorry, 60. Not the variable, but the constant 60. So let's just label this 60. I messed up the color, but let's just go on with this one. You have 60, H, and then S. That's a right triangle right there. Let me mark that with a marker here, which is just that one. Okay. So now, again, the first step is to find a relationship between the variables that you want to examine and then the given variables. That's usually the first task that you need to do. And obviously, since we got a right triangle, what we're going to do with that one is we're going to use the Pythagorean theorem. So for example, here, we're going to say s squared is equals to h squared plus 60 squared. Now, what's next to this? You have established the relationship between the variable that you're interested with and another variable that are given on the problem. Well, the next step is to perform the derivatives. Okay. So, but remember, we're talking about time rates here. So all of the derivatives now must be with respect to time, and nothing. We don't really need to worry about that because we've already done something like that on the first part of this discussion. So let's try that again below. So here, this will become 2s, but according to the chain rule, you need to take the derivative of the inside term. So this will become ds dt. Okay, now you're gonna do the same thing for h squared. This will become 2h times dh dt. And then, well, of course, the derivative of 60 squared is just 0 because it doesn't change. Now you can divide this by 2. And what do you get? Well, you get ds dt. The rate of separation with respect to time is just equals to h over s times the rate of h with respect to time. Now, this is the main part here. The next step here to this one is to plug in the values that you know about the right hand side. So here, you have to know some values here that is, well, it's coming from the given on the problem. First thing that we know is that we already have the rate of one of this. Or what I mean is the rate right here, h. That's the rate of the balloon, or the height of the balloon as it goes up over time. And that's given because on the problem, it was stated that the rate at which they go up is 10 feet per second. So we're going to say that according to the given, you have to take note that here, take note of that in here. So dh dt, the rate of the height with respect to time, is just equal to 10 feet per second. Now, when we solve, we usually don't include the units. It's a good practice to do so, but just to make our lives easier when doing this lecture, just not write the units first. Let's just be confident that the units will agree, well, in the end. Okay. And now, say we say that we have the value. So let me change the color first for consistency. We have here h over s, and then it's gonna be multiplied with 10. Problem doesn't state that the rate changes over time, so we assume that the dh dt is a constant value of 10 feet per second. Now, the next thing that you have to know is what's the value of h and what's the value of s. Well, you can find that from the problem itself, because the problem stated that we need to perform, or we need to measure the rate after 8 seconds. So that 8 seconds right there must play a role on finding the value of h and s. And in fact, it does. So after 8 seconds, something will happen. The balloon's height will change. And let's assume that the balloon started from the ground. So now you can find out that h after 8 seconds is just the speed of the balloon is 10 feet per second multiplied with the time that has passed. That is 8 seconds. So I'm putting units here. You don't need to. Let's just remove this one to be consistent with what we said. So now we say that the height of the balloon after 8 seconds is 80 feet. And that's it. You will have the value 80 feet. Now, next is you want to find the value of s, the separation after that. But you shouldn't really worry about that one because now we already got the relationship between s and h. We said that s squared is equals to h squared plus 60 squared. So now, if you want to find s, this is very simple because all you have to do is to take the square root of h squared plus 60 squared. You don't need to put plus minus because s should always be positive right here because this is physical distance. So now, here I got 80. squared plus 60 squared. And maybe we could find the value of s from that. What do you think that's the value of s? Well, if you take the square root of 80 squared plus 60 squared, that gives us the answer of 100 feet. So now we got these values, which allows us to now finally solve for our rate, which is the separation rate after 8 seconds. So we say ds dt is equals to, we'll get the value of 80 times 10. Let me change the parentheses here to make it larger. And then all of that divided by 100. Now, as you can see, that's just, well, 800 over 100. So for the final answer, we got the rate ds dt, which is just 8. Well, the unit here should agree with the other one, so it should be 80 feet per second. And that's telling us how fast are now the balloon and the observer separating after 8 seconds. And that's it. That's how time rates work, and that's how we find out that those quantities are most of the time related to each other. When I mean related to each other, I'm referring to S and H, so hence we call them related rates. So I hope with this example you get the idea on how to perform time rates. Okay, so for the proceeding discussions here, we're just really gonna proceed with other kinds of problems, and we're gonna see if how can we deduce the solution out from the given. So without further delay, let's talk about the other problem here, which is all about, well, still separation, but let's change up the theme from 2 dimensions into 3 dimensions. Let me just copy this again. Okay. So now I'm gonna try to paste it here. Hopefully it doesn't break anything here. Okay, so now let me just drag this down. Okay, there we go. And then let me delete this. Well, I have nothing to delete here. Okay, so now here is another problem. Okay, it talks about a man walking across a bridge at a rate of 5 feet per second. Doesn't specify the direction, but for our illustration, let's just assume that the man is going in this direction. If you can tell, this person right here, this one in blue, I moved the bridge. It's not supposed to happen, but here's a man here in blue. They're moving 5 feet per second, and this black person here, or black colored stick figure, represents now the future position of the the blue stick figure before. Okay, so now that's the man being described in this problem, and then below the man, after during the start, there's a boat that's directly beneath him that's going at the pace of 10 feet per second, and then again the direction was not specified, so we're just gonna assume that the direction is perpendicular to the direction of the man. That's the most likely scenario when you have a boat under the bridge. Well, not usually, but let's assume that one for simplicity. So they are moving perpendicular from each other. Okay, so now if the bridge is 30 feet above the water, or at least the platform where the man is standing upon over the boat is 30 feet, then the question is, how fast are the man and the boat separating after 3 seconds? So this is like the problem from before, but now we're dealing with 3 dimensions. When I say 3 dimensions, it's because of the fact that our distances, or the distances that we're going to consider now between the man and the boat, takes up 3 dimensions. What are those dimensions? I'm going to try to draw that for you. So here is one dimension, it's along the, perhaps let's call this the z-axis. Okay, and then another dimension is going to be the direction of your boat. And the third dimension that we're going to look at is the direction at which the person is going. Okay, now as you can tell, this person right here, sorry for that. Okay, so now what I'm trying to say is that the direction or the separation between the person and the boat now can be represented by a line segment. Let's just color it orange. That connects this portion right here to the position or the future position of the man. So those are 3-dimensional points, and then you want to measure the separation between them. Okay, so to put it simply, you got this illustration right here, which represents all the things that we talked about. So we can now reduce the representation of the man and the boat into points. When I say points, I'm referring to this one and as well as that one. Okay, they're 3D distance, 3-dimensional distance. Now, as I've said, you're gonna start with establishing first the needed relation between the variables that you're interested with. We are interested with the rate of s, the separation again. So now somehow we need to be able to find an expression that solves for s. And how do we even do that one? Well, for s, this is just another, we're measuring distance between points. And this point right here, for example, they are along the x-axis, they're separated by x distance. Along the y-axis, they're separated by the variable y. And along the z-axis, they're separated by the variable z. So now, how do you find the rate between them? So, for example, here, I'm saying, how do you find the distance between them? So, for example, here, we're going to do the same thing as the Pythagorean theorem. So, we can say s squared is just equals to the usual x squared plus y squared. But then, due to the added dimension, we also got z squared. And that's pretty much it. That's how we find the distances between these two things right here. Okay, so now I'm just going to pause this a bit. I'm just going to do something else. And I'm going to be back in a few seconds. Okay, I'm back. So now, as I'm saying, we can solve this one by establishing the equation here. S squared equals to x squared plus y squared plus z squared. This is just a three-dimensional version of the Pythagorean theorem. Okay, so now, the next thing to do is to solve for the derivatives, just like what we did. But before that, notice that z here represents the height of your bridge. And for most bridges, or just like this one, the height of the bridge doesn't change. Okay, so for that, we can say that instead of writing here z, we can just simply write s squared equals to x squared plus y squared, and just simply write 30 squared. This is like a previous example earlier where we got the value 60 feet. So we didn't put the variable x, for example, or y, or any other variable to represent the one because it's a constant. It doesn't change. No need to represent it with a variable. Okay, so that makes our lives easier because now we're just going to deal with 3 variables. And that's simple. Okay, so we're going to find the derivative of this the usual way. So we have here 2s. As you can tell, this will become ds dt. Then x squared becomes 2x dx dt. And then as well as your y squared, this becomes 2y dy dt. And then 30 squared becomes 0 because that's the derivative of a constant. Now, as well as this one, you can divide all of them by 2, so now you don't need the 2's in front. So remember, we're interested with ds dt. So all you have to do now is to take all of the values on the right side, you divide all of them by s. See, that's the variable in front of ds dt. Okay, so that will be x dx dt plus y dy dt. Okay, so now, what's next? Well, we need to figure out what are the rates that we know so far. Well, x represents the person's distance. Remember, x is in this direction, so it's going to talk about the position of the person, and y is along this direction. So according to this label right here, y is the direction of the boat, and that represents to the changes in the position of the boat. So now, if you think about it, your dx dt, I keep scrolling, but your dx dt right here is the rate of x with respect to time. And on the problem, the rate of the person with respect to time, or at least their movement with respect to time, is 5 feet per second. So also, you can tell that the rate of the boat is 10 feet per second. And what do we do with that information? Well, now, we say that your dx dt is 5 feet per second. I'm not sure, 5 feet per second. And then your dy dt, or the boat's rate, is 10 feet per second. And that's just pretty much it. We're going to put the values here. X times, well, it's 5. And then y. And we got to know that's just 10. And you divide all of them by s. So that is that we're completing the derivative piece by piece. We're putting in the information that we know so far. Okay, now next. The next thing we should know is what's the value of x, what's the value of y, and so what's the value of s. How do you find x, y, and s? Well, remember that these things are happening, or the rate that you're gonna measure is after 3 seconds. According to the problem, we're measuring after 3 seconds. That's a very bad. Well, I can't do anything about that. So after 3 seconds later, so you're gonna measure the rate after that one. So if you want to measure that rate, then all I have to do is to find out the x and y and s after 3 seconds. And that's not really a hard thing to do because you already have the rate of x and the rate of y. So if you want to find x, same thing as we did with the previous example, you got the speed of the person, you just multiply that with time. Make sure that if this is 5 feet per second, your time is also in seconds. Luckily for us, the given time is in seconds. That's 3 seconds. Okay? Remember, this is in the units of feet per second. So all the units there are agreeing to each other. Okay? So now that tells us that x is just 15. Now by the same logic, we can find that the distance of the boat after 3 seconds is just 10 times 3. And that's simply 30 feet. Okay? Let's put feet here to emphasize that's the unit of your distance. And now you can plug in the values. So you have here x as 15 times 5 plus y, that's 30. Multiply that with 10. And you divide by s. But the question is, what's the value of s? Okay, now if you think about this, we don't have a value for s yet because we don't have the rate of s, because in the first place, that's a problem that's the value that we're looking for. But luckily for us, since we have established the equation earlier that we said s squared is just equal to x squared plus y squared plus 30 squared, then we can find s from that one. So how so? So for that, all you need to do is to just take the square root of the right side of the said equation. So you have here x squared plus y squared plus 30 squared. And now, since we already have the value of x and y after 3 seconds, we're just going to put them in there. That's 15 squared plus 30 squared plus another 30 squared. And what's the value for that? Well, the value for that is given by the value 45 feet. I'm looking at my notes if you're wondering why is it I'm solving so fast. I'm just really looking at the notes on the other screen. So that's over 45 feet. And now we can find the result of this. So we have DSTT. You can use your calculator for this or do this mentally. I cannot do it mentally, so we do this. I'm just going to take a look at my notes. And the answer for this is 8.333. I think it's a repeating value. Let's just put something like that. And then the unit is feet per second. And that's it. That's the rate at which the man and the boat are separating after 3 seconds. Okay? Now, you can get a lot of insights from this. Perhaps you can even guess how are they separating after a long time. Will the rate of their separation decrease or increase when they are far apart? Or is it going to increase when they're closer? Or where is it faster? Why is the separation faster? Is it when they're closer or when they're further apart? Okay, things like that. But for now, we're going to limit our discussion into that calculation right there. We found out that the rate of separation after 3 seconds is 8.333, repeating value of decimals after the said time. Okay, so I hope that's clear. Okay, so now, as a change of pace, we're going to talk about another example here, which is an example that is more geometric in nature, in a sense that now we're talking about shapes. We're going to talk about 3-dimensional shapes. In this example, we're going to talk about a tank, a water tank. So a water tank is in the shape of a cone. So let's just put it here. Something like that. So for those of you who have done a lot of things on maybe your childhood, you probably noticed that when you fill up a cone, it will be filling up faster when it's on the bottom, and then it gets slower and slower and gets to the top. And we're gonna try to see why is that happening on us, or why does that happen in a cone? Why is it that it's filling up faster when it's down below, and when the water is up top, it rises slower and slower? And in fact, that's the main goal of this problem. We're talking about this scenario here where a water is flowing into a conical reservoir. where the depth of the conical reservoir is 20 feet according to this figure, and the diameter across the top of the cone is 10 feet per second. Now, the rate of the water entering here is 5 cubic feet per minute. And then you wish to know how fast is the water level rising when the water is 8 feet deep. So this is one of the things that if you don't have a direct measurement of the height of the fluid and you want to measure the rate at which they are rising, and all you have is the rate of the water flow, then here it's a very good example of related rates, because even though you don't have a direct measure for the rate that you're looking for, but since you have a measure of the rate that affects the other one, then it's possible for us, or possible for you, perhaps when you're an engineer or when a designer someday, to find out or to quantify the rate of, well, the related variable. And that rate here is the height of the water. Okay, so in this figure, you can see that we are putting here the dimensions. You can see that 10 feet now has become 5 feet, which represents not the diameter but the radius of the cone, the base of the cone, and then the height here is indicated as 20 feet. Now we also introduced some variables. According to this, we introduced the variable r and h. If you can see this one, this is r, the radius, and then the height of the water. Those are kept as variables because, as you can see, this water level will change over time, and that's the general rule. If it's changing, put a variable. If it's not, then just put the number of the constant value. Okay, now for this one, we need to know what we want. We want to know how fast is the water level rising, and what is that quantity? Well, that is your rate of the height with respect to time. So that's dH dt. So we need to find this one. Okay, but we are given things. When I say things, we're given some rates. For example, we are given 15 cubic feet per minute. And remember, cubic units are representative of volumes. So we say this rate is just the same as the rate of the volume with respect to time. Remember here, time is in minutes. Okay, so that's it. So we're looking for dH dt, and we're given dV dt. It's also given that we need to find your dH dt when, let me just remove the circles here. We need to find dH dt when the height of the water is equals to 8 feet. Okay, so this is not the time that's given. So we're not talking about after 3 seconds, after 8 seconds, but rather after or during at the time when your height is equals to 8 feet. Okay, so now how do we do this one? So first, we're gonna need to find a relationship between the thing that you want and the variable that's given on the problem. So we're given the volume rate, the rate of the water flow, and then we want to find the rate of the height. And one way to do that one, to relate them, is to find the formula for the volume of a cone. Now before that, let's talk about what are the volume of general cones. So when you have a cone, when you have cones rather, so typically cones can be drawn like this. So I'm just gonna really just put some values here, perhaps something like that, and then I'm just gonna use some ellipse here. Okay, so let's just pray that this is gonna align with the other parts. Okay, so perhaps something like that. Now when you have this kinds of things in a cone, just imagine this is a cone. What will happen when you wanna find the volume of these things is that you're just gonna really be interested with this part right here, and then the area right here. Let's put the A. Okay, and then let's just say that the height is, well, h, the height of the cone. Now I'm drawing it this way because I want to point out, I want to emphasize that the cones can be slanted. Okay, so it's not necessary to have your peaks or your apex to be directly above the center of your base. I'm putting a lot of sigmas here to emphasize that this is a cone, but if you can imagine that this is indeed a cone. Okay, so now what is the volume of any cones? Well, the volume of any cones is simply given by the formula 1/3 the area down below indicated by A, and then times the height of the cone. And height is just measured from the apex, or the highest point of your cone, down to the base. It's the perpendicular distance between the point and then the plane at which your base lies at. Okay, so this is good because we have a general understanding of what is the volume of your cones. Now, before going on to our main problem, I just want to emphasize also that this formula, this one right here, formula for the cone even works for, well, things that are not cones, but like cones. For example, we can find the volume of the pyramids in the same way. So, for example, if you have a rectangular pyramid, the base is a rectangle, then the formula is still the same. And what will change here? Well, it's just the shape of your base. You're still gonna consider the height of the pyramid from the apex directly below to the plane of your base and things like that. So you're just gonna think about what's the area of the base and then what's the height. So now, since our cone is illustrated above, it's just a cone, regular cone, where your apex is just, well, in this case, directly below the base. Then the formula is simply just this one. Okay, the height is just the height of the water, and then the base can be found from the shape of the base. The shape of the base is a circle, and the area for a circle is simply given by pi r squared. So therefore, our volume for the cone, so we're not talking about the cone in our problem, it's just 1/3 pi r squared times h. Now remember, this is the volume of the water, not the whole cone. We don't consider the volume of the whole container because remember, we're interested with the surface of the water. So the water is only up to this blue shaded region right there. Okay? So now, what's the next step here? Well, the next step is, well, there are many approaches to this. One approach is to just solve this expression in terms of finding their derivatives with respect to time, where here you can see that r is a variable, h is a variable. So most likely what you'll do here is to use implicit you're gonna use here the product rule, but that would expand our terms. So what I suggest here is to actually make an effort to change this one into v, where it's just a function of h. What it means is that on the right side, this will only contain h terms. Why? Well, because we wanted to know the rate of your height. So your values must be with respect to your values must be h with respect to time in the end. So you should get the derivative dh dt. Okay, so now how do we achieve that one? So to achieve that one, we're gonna take a look at the cross section of our cone. In the cross section of that one, you can see that there is, okay, let me just try to make a straight line here. So it's 6, the shortcut is 6. Okay, so here you have a triangle. I have to keep pressing 6 whenever I add the line, and that's not convenient. Okay, so yeah, let's just freehand this one. Okay, excuse me for this drawing, but we have no choice. Okay, let's just say this is a right triangle, and then sure, if we have a perfectly level tank, then also this smaller water line here would make another smaller right triangle. I say smaller because it's obviously smaller from the figure. And then that is handy because now we can label some units here. We know that the height of your tank is 20 feet. This is 5 feet, the radius of your base. We don't know this one, let's call it R. We don't know this one, let's call this H. Now, this calls for using your similar triangles. When I say similar triangles, there's our triangles inside other triangles where the ratio of their lengths are the same. So I'm referring to this one. So I've fully given up with lines. I'm just going to draw it freehand here. Hopefully you can still see what I'm referring to here because I'm not really good with drawing here. So 5 feet and 20 feet. That's the larger triangle. And then the smaller triangle is this one right here. You have R and then you have H. So what about this? Well, again, they are similar triangles. So when you divide their lengths, the ratio must be the same. So you have here 20 over 5. And that's going to correspond to H over R. So perhaps you solve this one, you get 4, you get H over R. and solving for r, that clearly gives us the value h over 4. Now, why do we solve for r? Well, that is done because remember what we wanted is to just have h terms. So we're going to take advantage of r being h equals to 4 and replace our value of r here so that all of the variables on the right side for our volume is now all with respect to the height. So what does that give us? Well, it gives us the fact that we started with this one, 1/3 by r squared h. It will now become v equals to the volume equals to 1/3 pi, but r now becomes h over 4 squared and then h. So our volume equation can now be written as pi, and then there are 3 h's there being multiplied, so that's h cubed all over 3 times 4 squared is 16, and I believe 4 squared times 16 is, well, that is 48, I think. Yeah, I'm gonna say that's wrong. It's not 4 squared times 16, but 3 times what do you call this one? 3 times 16. So let me just verify that with a calculator right here. 3 times 16. I'm really good with arithmetic. Yeah, that's 48. Okay, so now that's our formula for the volume. And isn't that a lot easier? Because now, when you want to find out what's the derivative dv dt, then that's going to be pi over 48, and then times 3h squared. And don't forget the chain rule, dh dt. It's a good move that we didn't just... it would have been fine if we didn't just multiply 3 and 16 earlier, because as you can tell, we're just gonna divide by 3 on both sides. So this will become 16 again. So now if you want to find dh dt, it's just gonna be dv dt all over pi h squared all over 16. And then what do we know so far? Well, we know some rates. Again, as we said, the dv dt is the rate of the volume, and we know that it's just equals to the given, which is if I can recall, that is I cannot recall, so let's just scroll up. So that's 15 cubic feet per minute. So we say dv dt is 15, and then we also said, or the problem said, that we want to measure the rate during the height, well, when the height is 8 feet. So we're gonna specify there that the height is 8. So in particular, we got this values covered already because we already have the needed things in there. So we find dh dt is just equal to 15 over pi times 8 squared over 16. And when you plug this into your calculator, you should get the following value. You have dh dt is equals to 1.194 feet per minute. And that's the rate now of your height after the height reaches 8 feet. Okay, so that's our answer right there. But I think the most important output from this calculation is the fact that when you think about this one, you think about this equation right here, I'm referring to this one, you can see that on this illustration right there, h is down below. It's on the denominator. And what does that mean? Well, since the volume rate doesn't change, it's always going to be 15. Pi is a constant, 16 is constant. So only h or the h variable will change over time. And when it changes, when it becomes larger, the denominator becomes larger. So this part right here becomes large. And what does that imply? Well, when it's large, the total quantity of this fraction reduces, thereby also reducing the rate of height with respect to time, or the surface height with respect to time. And that's the reason why we said earlier that when you fill up a cone, it's faster to rise down below than when it is closest to the top of your container. And I guess that's the beautiful thing about this, because now you can put your deductions or your observations into a more pure mathematical proof of doing so. Okay, so that's one example down for a liquid filling up a tank. Now, perhaps for the last example in this discussion, I want to talk to you about an example here where we're going to talk about some quantities, and we're going to consider when is it to have a negative rate and a positive rate. And we can illustrate that one with an example that I'm going to copy from the other screen. So here, we're talking about a rate, which is, according to this, we're talking about a rate that's focused on the shadow of a person moving. I forgot to copy the question statement, so let me just go back here and copy the question. So I should have prepared a PowerPoint for this, but I think it's we're doing this spontaneously. So here, so we have here a light at eye level stands 20 feet from a house. So we're referring to this green yellowish thing right here. I think I've messed up copying the label. I'm just gonna copy this here. It's the light for this house. So it is 20 feet from the wall of the house, and it's 15 feet away from the pathway directly towards the house. It so happened that during that time, in person, this one labeled by this dot, I can't really draw a person, but there's a person right here. They're moving towards the house perpendicular to the wall. And then the question is, how fast do you think is the rate? How fast do you think is the shadow of the person, the shadow that's being casted in this direction, going to move when the person is 5 feet away from the house? Those are a lot of things, but essentially, when you imagine this one, when the person is far away from the wall, so when the person is standing, perhaps right here, let me just get the color red. We were using red here. So the person is standing up here, or perhaps right here. You can tell that the ray being casted or the shadow being casted is just, well, it's far away. It's somewhere here. And then in some ways, you should also know that when the person gets closer and closer. So for example, it's not anymore here, but it's not anymore here, but maybe somewhere here. Then the shadow will get closer and closer to the walkway, or the direction towards the walkway intersects with the wall of the house. So the question is, how fast will this shadow move at the said condition? Well, here we can make predictions about the result. So since we know, or at least for this problem, we've used some variables to indicate things that are involved. So for example, we said that the distance of the shadow from the walkway is s, and the distance of the person from the wall is x. Notice that when the person gets closer, this distance is decreasing. Okay? And in the same manner, your s will also decrease, because as we illustrated earlier, as the person gets closer and closer to the wall, the person and the shadow will eventually meet at this junction right here. So both of the quantities are decreasing. Now, why is that important to know? It's important because when you say decreasing, that means that the rate that you are looking for should be less than 0 or negative, because negative derivatives represents decreasing values in functions or in quantities. When your rate is negative, it doesn't mean that their value is, well, it's taking up the other side of the x-axis, but rather essentially it means that the quantity it represents is reducing in terms of its value. Okay, that may be a different scenario for things that are truly gonna cover the negative values. For example, when you're talking about integers, they have negative values, but when you talk about mass having a negative rate, or height having a negative rate, or distance having a negative rate, it doesn't mean that the height, the mass, and things like that are negative, but rather they are reducing. So I hope I made my point. Okay, so now the usual way. So what's the usual way to solve this one? First, you're gonna establish the rate that you want, and then find a way to relate that in some kind of equation that is gonna utilize the other variables in this problem. Remember, we're looking for the rate at which the shadow move. Okay, and then here we are given a few things. We're given the rate of the person, or at least the movement of the person. That's dxdt. It's equals to, well, according to the problem, it's 6 feet per second. Okay, but remember, x here, the variable representing the person's distance from the wall is decreasing. So therefore, you have to be careful with the rate that we specify. It's not just x, but rather negative. Sorry, it's not just 6, but negative 6. Sorry for that. Okay, so that's a messed up. Sorry. Okay, now. Okay, so now. So you have negative 6. That's a decreasing value. I'm sorry, I can't stop now. I'm distracted by that one. I apologize for that one. It's not intentional. Okay, so anyway, that's negative 6. And your dx dt is decreasing, so you put negative in front of it. Now, so we need to find a way to relate your variable s with and x. So the way to do that is, again, look at triangles. Triangles are really the answers for these kinds of things. So how do you do that one? Well, let's draw a separate triangle here. That is a right triangle, assuming that your light and then your walkways are directly perpendicular to the wall. Okay, so what happens now? Well, here you get 20 feet. And then here you get, well, it's given that the distance of the pathway is 15. So we're going to specify here 15. And then also we're going to specify that this one is S. So it's a bit larger than the drawing earlier, but remember, this will change over time. So it doesn't really mean much because it will change over time. Okay, let's call this X. Remember, this is the ray from the light source. Okay, so this 20 feet will not change because the light is fixed in there. This 15 will not change because, of course, your pathway is not moving closer and further from the line between the wall and the light. Okay, so how does this help us? Because now is this triangle is another source of similar triangles. When we see similar triangles, we have the bigger version and then the smaller version of the rectangles. You get 15 plus S, and you get 20 right there. Okay, that's the larger triangle. It's 15 plus S. How about the smaller one? Okay, the smaller one has the length S and then X. So according to what we said, whenever you have similar triangles, you can just divide the sides and it's guaranteed that their ratios are equal. So you have your S plus 15 over 20. That's the same thing as S over X. Okay, so now we have established an equation where you can relate both the variable S and the variable X. So what's next? Well, next thing is you can simplify this a bit. Maybe you can multiply both sides by 20. Okay, to get rid of the 20 denominator here, just get rid of that. Then essentially you have S plus 15, and then you probably have 20. And not probably, but you get, well, that is 20S over X. Next, maybe you can cross multiply. You get SX plus 15X equals to 20S. Okay, so you might ask, what's next? Well, the usual. We're gonna find the derivative or the time derivatives of all of these terms right here. So how do you do so? Well, here this requires us to do the product rule. So we're gonna do that one. We're gonna have ds. It's product rule. So usually we do s, the first variable, times the variable of the other one, the derivative of the other one rather. That's dx dt plus x, and this time is the s derivative. So we have ds dt. So we're done with that part. We now have the derivative of this one. But now the next thing you'll do is the derivative of 15x. That's gonna be 15 dx dt. And now we have 20 times ds dt. Okay, so what's next? Well, we're interested with the rate of the shadow. So we're gonna put together all of the ds dt's in one side and all of the things that we don't need on the other side. So perhaps we can do this one. I got x plus 20 ds dt, and all of the things that we don't need, those things that have dx dt's, will have to move on the other side. That's essentially s plus 15 dx dt. So we wanted to know what is ds dt given. We wanted to know what is ds dt, so we just divide both sides by x plus 20. So we got s plus 15 dx dt, and then that's all over x plus 20. Okay, so now let's take a look at the available values for us. Well, first, we know dxdt, that's the speed of the person. The person is moving at the rate of, we said earlier, your dxdt is negative 6. So we stated that one earlier. So negative 6 because, again, it is decreasing. Okay, as well as the fact that now, when you want to solve for this scattered kinds of things, you could also solve for s and x. So how about the value of x? Where do we get the value of x? Well, according to the problem, we are interested at the rate when x is equals to 5 feet from the house. Now, do we write negative 5 here? Well, not, because x is not a rate. It represents the actual distance from the wall of the house and then the person. So after that, we need to find the value of s. So what is s? Well, you get the value of s from the equation that we made earlier. So perhaps, let's see what is the simplest one here. Well, there's not that much simple. So maybe we can just rewrite this part right here to find the value of s. So here, what I'll do is this. I'm going to group together all of the s terms. Okay, perhaps we're going to get s x minus 20s and get negative 15x. And then here we get s times x minus 20 equals to negative 15x. Okay, so dividing both sides by x minus 20, you get negative 15x over x minus 20. Okay, so to find s, therefore, you just need to plug in the values of x. So here you get negative 15 times 5 all over 5 minus 20. And I don't know if I have an answer for this. I'm not sure. But let's just say, or use your calculator to plug in those values. I'm not good with arithmetic, so we're going to have to go through this one. So you have your negative 15 times 5. I'm not sure if I'm putting the numbers correctly, but you can see on the screen, you have negative 15. And then that's it. Now you have the value of 5 as well. Well, we put here the value is also 5 feet. Is it feet? Yes, indeed. They're using feet and then seconds. Okay, so now we got all of the values that we need. So what's next? So we're now going to put some values right here. Now, what I'm afraid here is I think I messed up some signs. We're going to see later. We're just going to solve this one. We're going to examine where did we go wrong. But here we got the s, which is 5. And then plus 15. And you got x is also 5. It's 20. And then your dxdt is negative 6. So notice that I'm saying that we might have something messed up here, or we messed up something here, because now, as you can tell, this value right here is negative times negative. That gives us the value of s, which is dsdt, that is positive. Which what we wanted earlier is that dsdt should also be negative because it's also decreasing. So let's examine first where did we go wrong with this one. Well, I think I know where we went wrong with this. I think it has to do with this part right here. It should have been for those of keen eyes, this should have been negative 20, because remember we're moving this in here. Okay, so yeah, that's a mistake right there. So let's just correct our mistake before solving for the final answer. Okay, so now let me just fix this one. This is minus 20, and it gives us a negative value on the denominator. Okay, so we have 5 minus 20. And hopefully that fixes things up, because I cannot know what are the other mistakes here if that's not the mistake. Okay, let me open up the calculator again. For this one, we're going to plug in our values. Let me zoom in here. So we got, forgive me for having to do this one. I'm not confident with my arithmetic skills. So we're just going to write it this way. 5 plus 15, those are all negative, times negative 6, all over negative 15. Well, let's see. The answer is now negative 8. And that kind of makes sense. It's a whole number. It's a good sign. I'm not saying it has to be a whole number, but usually when you see a whole number, it's a good sign in solving mathematics. So if you're negative 8 feet per second. So that aligns with our prediction that the shadow also, or the distance between the shadow and the position that we mentioned right here, this one right here, should be decreasing. Hence, we get negative 8 feet per second. And that's the answer for this one. So during the time when the man is 5 feet away from the house, then the rate at which the shadow moves is 8 feet per second. Notice that this tells us that the speed of the shadow is faster than the speed of the man himself. So yeah, that's interesting. So maybe you can use this not just for a person moving, a fictional person moving, but maybe for things like ray tracing. You wanna see how the ray moves in a graphical graphical simulation. Perhaps you're simulating rays of lights, then it's possible to know the speed of the rays, whatever. That's if you wanted to know the speed of the rays in your it could be a researcher, things like that. I'm not sure. I'm just really rambling things about this one. But anyway, I hope you get my point. So it's now possible for us to find a rate that's related to the person moving. In this case, we're talking about the shadow of this person. Now, we have been recording for how long? I don't know. Let me check. So this is about an hour. I'm just gonna add one more example here to show you a difference between approaches. So we might have different answers, or I'm sorry, we might have different approaches to the same problem. So here, what I'm gonna do for the last example is that we're gonna solve a problem that's related to the shadow problem. In fact, it's a lot simpler. But what we're gonna do is we're gonna solve it in two ways. Okay, so what are those ways? Well, let's take a look at this one first. So, okay, sorry. Let me just paste it again. Okay, so I think I'm pressing the wrong key. So let me just paste this one. Is it this? It's this. Okay, so according to this problem, you have here a ladder 20 feet long leans against a vertical wall. So as you can see, the ladder's there. This one in blue. Now, if the top slides downward, so it goes down below, so indicated by the arrow, at a rate of 2 feet per second, find how fast the lower end is gonna move away from the wall when it is 16 feet. So when the time it is 16 feet, how fast is this going? Okay, so at this point, I think we're pretty much we pretty much know what to do with this one. We first establish the equation. So we have here x squared plus y squared is gonna be always equal to 20 squared. Where is this from? Well, that's coming from the right triangle that you can see in there. Okay, now before taking the derivatives, let us set our expectation. You can see that y, or the height of the top part of the ladder with respect to the ground, is decreasing. So therefore, when you want to write dy dt, you're not going to say that it's just positive 2 feet per second, but rather negative 2 feet per second. What's the reason? Well, the reason is that this is representing a value that is decreasing. Okay, again, let's just put it here. This is decreasing. Okay. On the other end, x is increasing. So therefore, our expectations of dx dt, the rate of x, or the lower part from as it moves from the wall, should be greater than 0. Okay, because it is again increasing. Okay. Okay, so now let's solve this one. Now that we have our expectations, we're gonna find the time rates here by taking the derivatives. You have here 2x plus dx dt times dx dt rather. You have 2y dy dt. And this makes our derivative simple because this is just equals to 0. 20 squared is constant. Divide by 2. So we're interested with dx dt. And now, as you can see, this one becomes negative y dy dt all over, excuse me, okay, all over negative y dy dt all over x. Okay, where's x come from? It's coming from this part right here. Okay, so now let's plug in the values that we know. We know dy dt. Dy dt is given by negative 2. So we put here negative 2. We also know the value of x. We said that find how fast the lower end is moving when it is 16 feet from the wall. This word it here, okay, represents the lower end of the ladder. So that is representative of the variable x. That's 16 feet. And then again, we don't put negative here because we are talking about the length of x, not the rate of x. We have a negative sign here by default because we transferred the term from the other side. Okay, so that's negative. But now we need to find the value of y. Where do we get the value of y? Well, it's coming from the Pythagorean theorem. So we say y is equal to the square root of 20 squared minus x squared. That gives us 20 squared minus 16 squared. And with that, we can find the y value. Let me see if I have a prepared solution here. Well, according to this, y is just 12 feet. Okay, so you plug in the value of 12 and that's it. We already got the values and we can find our dx dt. Okay, so what is dx dt? So it's now positive 1.5 feet per second. Okay, now this example is, well, it's the usual example that we had. This is a lot simpler than the previous one, that's sure. But now, well, my point in doing this one is I want to tell you about another way to solve this one. Okay, what's the other way? Well, the other way, to just give you a perspective in solving these kinds of things, could be through trigonometry. Okay, so we don't need to limit ourselves to Pythagorean theorem. Well, I say Pythagorean theorem is simpler, but maybe it's a lot quicker when we do it using the trigonometric functions. So how do we do so? Well, things like this can be done by, again, examining our triangle. Let me redraw the triangle here. So let me just say, let me just put here via, okay, trigonometric functions. Yeah. Okay, so now how do we solve this one via trigonometric functions? So here is what we'll do. We're gonna need another equation. Okay, where's my triangle here? Okay, I think I've erased my triangle. Let me draw the triangle here. So we're gonna need a triangle that involves trigonometric functions, that's for sure. Okay, so we get 20 feet here. This is our variable y, this is the variable x, and then also we got the variable, well, let's say this is theta. Okay, so in terms of trigonometric functions, we're gonna need variables that are representative of angles. Now, do we need y? That's a question. Well, let's see. So here we can find, we can relate y by solving this. We can say sine of theta is just equals to y over 20, and that wouldn't change because 20 is a fixed number. So we can see that when theta changes, the y also change, or vice versa. When y changes, theta will also change. And now, as you can see, if you want to relate dy, remember that the given value that we had, dy dt, is -2. If you want to find out how is this related to theta, then I'll have to do the usual things that we do. We find the rate of theta. So we have here, if you want to take the derivative of this, when we know the derivative of cosine, or sine is cosine, and then with the chain rule, this will become d theta dt. Okay, I'm referring to the derivative of theta. Okay, but now we have 1 over 20, and remember the derivative of y is dy dt. Okay, so now what does this tell us? Well, this is just an indirect way of solving for dx dt by solving first for d theta dt. And what is the answer for this? Well, you have here 1 over 20, and then this one is dy dt, that's -2. That's the value that we got earlier. And then also we got 1 over cosine of theta. Okay, you can say that it's just the second function, but for the sake of simplicity, let's just put it right there, d theta dt. So this one becomes, well, 1 and then 10. So this is -1 over 10 cosine of theta. Okay, so here, so at 16 feet, okay, so we said that everything here happens when x is at 16 feet. So we have 16 here. And then we also got, well, here, we also know this is 20 and this is theta. We wish to know what is cosine of theta. Now, to know cosine of theta, it could be done by solving for y. I'm sorry, it could be done by solving for the inverse trigonometric functions, using inverse trigonometric functions. But the best way here is to make use of 16, because now if I say cosine of theta, remember that 16 is the adjacent side of theta, 16 over 20. And I don't need to solve for the actual angle here. I'm just going to say cosine of theta. We're going to divide them by 4. This becomes 4. This becomes 5. So I know that cosine of theta is 4 over 5. That's that d theta dt is equals to negative 1 over 10 times 4 over 5. Okay, 4 over 5. And now this tells us that the value is 5, negative 5 over 40, or negative 1 over 8. Why negative? Because remember, as the top part of the ladder goes down, the angle will reduce. So that is decreasing. Okay? So that's negative. And that makes sense. Now, what's next? Well, we need to find dx dt. So how do you find that one? So dx dt, you can find that with, well, the relationship between your the relationship of x and theta. How do you relate x and theta? Well, you could use cosine of theta is equals to 60 x, sorry, not 16, but x over 20. I think I messed this up. I think we could have done this easily by solving for the derivative of cosine. Well, let's just stick with this one. Let's just change of perspective here. Not justifying this, but I think it could have been done better. But at least now we got the value d theta dt. We got to know the angular rate. Or is it that the problem is looking for that in the first place? Let me see. Okay, it's the same question. Okay, it's the same question. So it means that the answer should not be d theta dt. Is it the case? Well, yes. No, I was trying to verify if the question is actually asking for the angular rate, not the dx dt. But let's see. So here, I think this could have been done easier if we just well, solve for this in the first place. So let's see. This would become negative sine of theta d theta dt. It will become 1 over 20 times dx dt. Well, I think this would have been easier if we did this in the first place. Anyway, I apologize for this. Let's just stick with this one first. So here we got 1 over 20. And then, well, you have here, no. We're looking for dx dt, so we need to multiply 20 on the other side. It's negative 20 sine theta d theta dt. Remember, we already get the value of this is negative 1 over 8. So we just need to find, well, sine of theta. Let's just find that on the next line. Get negative 1 over 8. And remember, the way that you would check your answer is that it should match with the previous answer. So where do we get sine of theta? Well, sine of theta can be obtained using the similar technique here. Okay? But on the previous problem, we found that this is just, using the Pythagorean theorem, we found that this is just 12, I think. Is that 12? Yeah, it's 12. Okay, 12 feet. So now, if you wish to find, okay, let me hide this one. If I can hide this one. I'm not really sure. So let me just move this around here. So if we want to find sine of theta, that's now the opposite over the hypotenuse. So therefore, sine of theta is, well, you can divide this by 4. This becomes 3. This becomes 5. So now sine of theta is just equals to negative 23 over 5 times negative 1 over 8. And then here you have negative dx dt. So negative, well, negative 20 times 3 times negative 1 is positive 60, I think. And then 5 times 8 is 40. And then what's our answer before? It's 1.5. Well, that makes sense because this one is 6. This could divide all of them by 20. So this becomes 3 and this becomes 2. So I think we got the correct answer now. dx dt is still 1.5 feet per second. It seems like my apologies earlier were wasted because I think we also need to find out what is d theta dt from in the first place. So it's not really that straightforward when doing this one. I hope you can evaluate this for yourself. But this solution right here using trigonometric functions, I think it's a lot longer, I think, than the previous one. So not really recommended, but it's a good way to demonstrate that the solutions is not really just a single approach. It's not always the Pythagorean theorem, but you can think of other rates as long as they are all related. As you can see, theta, or the angle between the ground and the ladder, is directly related to your x and then y. So that paves a way for us to solve the rates even if we're not using the Pythagorean theorem. And I guess I can end the discussion now with this one. I hope you check out the other examples here. I've skipped some examples to save time, although we're not really saving time at 1 and 14. 1 hour and 14 minutes. But I guess that's it for this one. If you have questions, feel free to message me. This will be posted. This will be posted in your Google Classroom as well. Kind of check this one, this lecture right here. And then also, your notes for this are already posted in Google Classroom ahead of time. You can check this one, that one right there. The only thing is that some of these solutions might not be the same with the material that I've said, because that's an old material. I think the solutions here are updated compared to those ones. So some of the solutions might be a bit different. So kind of check what are the differences. Maybe some of these are better. Some of the solutions there are better than this. So you be the judge. But if you have questions, feel free to message me. And that's it for this discussion.